Hello everyone. Today we are going to analyze this beam using flexibility matrix method. In this beam, the support B sinks by 10 mm. The flexural rigidity EI is given as 8000 kN meter square. Before analyzing, let us see the beam one time. In this beam, there are two spans, span AB and span BC. In the span AB, there is a uniformly distributed load 3 kN per meter and it is acting for the full span. In the span BC, we have a eccentric point load 12.5 kN acting at 4 meter from the point B. The moment of inertia for the span AB is I. For the span BC, it is 2.5 I. Length of the span AB is 8 meter. Length of the span BC is 10 meter. In the point A, there is a fixed support. In the points B and C, there are roller supports. Now, let us find the static indeterminacy of the structure. In this beam, the number of unknown reactions and moments are 4. They are MA, RA, RB and RC. The available equilibrium equations are 2. Sigma M is equal to 0 and sigma V is equal to 0. So the degree of static indeterminacy is equal to 4 minus 2. We will get 2. We know that the support B is sinking. In the sinking or settlement type problems, we have to always release the vertical reactions. Let us release the vertical reactions RB and RC. When we release RB and RC from this continuous beam, this continuous beam becomes a cantilever beam. This cantilever beam is called released structure. We have made the released structure. Now let us make the coordinates diagram. In this analysis, there are two coordinates. We are having the coordinates in the points B and C. Because in these points only, we have removed the supports. Now let us see the formula to find the reactions. P matrix is equal to delta matrix inverse into delta matrix minus delta L matrix. Inside the P matrix, delta L matrix and delta matrix, there will be two values. Because in this analysis, there are two coordinates. We are having the coordinates in the points B and C. Since we have two coordinates, the size of the delta matrix will be 2 cross 2. Inside the P matrix, we will have RB and RC. In this formula, now let us find delta matrix. We know that inside the delta matrix, we will have the final displacements. Inside the delta matrix, we have delta 1 and delta 2. Delta 1 represents the first coordinate. Our first coordinate is in the point B. The support in the point B sinks by 10 mm. Let us convert 10 mm into meter. When we divide 10 by 1000, we will get in meter 0.01 meter. But inside the matrix, we have to apply as negative because the settlement occurs downwards. Now let us find delta 2. Delta 2 represents the second coordinate. Our second coordinate is in the point C. In the point C, there is no sinking. So delta 2 will be 0. In this formula, we have found delta matrix. Now we are going to find delta matrix and delta L matrix. To find them, we are going to use unit load method. In the unit load method, we have to find M, M1 and M2. Using the loads given in the question, we have to find M. Then we have to apply unit load in the coordinates. Our first coordinate is in the point B. So in the point B, we have to apply unit load and find M1. And then we have to apply unit load in the second coordinate. Then we have to find M2. Now let us find M. To find the moments, we have to make sections. In this beam, there are three different parts: CD, DB and BA. So we have to make three sections. You can see that I have made three sections. The first section in CD, the second section in DB, the third section in BA. Before calculating the moments in the sections, let us make the free body diagram so that we can easily find the moments. In the point B, let us split the beam into two parts, AB and BC. In BC, there is a point load 12.5 kN. Because of this point load, a reaction is created in the point B. Since the point load is acting downwards, the reaction should be acting upwards. Let us calculate the moment in the point B. This load is acting in the clockwise direction and the distance is 4 meter. 12.5 into 4, we will get 50. Since the load is acting in the clockwise direction, the developed movement in the point B should be acting in the anti-clockwise direction. On the right side in the point B, we have the reaction acting upwards. So in the left side, it should be acting downwards. On the right side, the movement is acting in the anti-clockwise direction. So on the left side, it should be acting in the clockwise direction. Now let us take BC and find the movement. We have made two sections in BC. I have made the first section at a distance of x from the point C. The second section also at a distance of x from the point C. First, let us take the member CD. For CD, the origin of the section is C. The limits are 0 to 6. In the span BC, the moment of inertia is 2.5 I. So the flexural rigidity for CD and DB will be 2.5 EI. So to get flexural rigidity, we have to multiply the moment of inertia with the Young's modulus. Now let us find the moment for CD. We are going to find the moment about the section from the point C. In this case, we are moving towards left hand side. Clockwise will be negative and anti-clockwise will be positive. Up to the first section, there is no load. So the moment will be 0. Now let us take dB. In dB, we have a section. The origin of the section is in the point C. The limit is 6 to 10. Now let us find the moment m in dB. Up to the section, there is only one load, that is 12.5 kN. This is acting in the clockwise direction, so it will be negative. For the distance, we have to take this distance. This distance is x minus 6. Now let us take BA. I have made the third section at a distance of x from the point B. So the origin of the section is the point B. The limit is 0 to 8. The flexural rigidity is EI. Now let us find the moment in the section. This 12.5 kilonewton is acting in the clockwise direction, so it will be negative and the distance is x. The UDL is also acting in the clockwise direction, so it is also negative. For the UDL, we have to multiply with the distance and distance by 2. Here the distance is x, so minus 3 into x by 2. The moment is acting in the clockwise direction, so it is also negative. X into x, we will get x square. 3 upon 2, we will get 1.5. Now we are going to find the moment m1. For that, we have to remove all of the loads and apply unit load in the first coordinate. Our first coordinate is in the point B. So here I have applied unit load. Then we can make the free body diagram. Let us assume that the unit load is applied just left of B. So we don't have to consider the right side. Now let us find the moment for CD and DB. Up to the first section and the second section, there is no load. So for CD and DB, M1 will be 0. Now let us find M1 for BA. Up to the section, we have only one load, that is the unit load. This unit load is acting in the anti-clockwise direction, so it will be positive and the distance is x. 1 into x, we will get x. Now we are going to find the moment m2. For that, we have to apply unit load in the second coordinate. After that, let us make the free body diagram. This load is acting upwards, so a reaction is created in the point B downwards. Now let us find the moment in the point B. This load is acting in the anti-clockwise direction and the distance is 10 meter. 1 into 10, we will get 10. Since this load is acting in the anti-clockwise direction, the developed moment in the point B should be acting in the clockwise direction. On the right side in the point B, unit load is acting downwards. So in the left side, it should be acting upwards. On the right side, the movement is acting in the clockwise direction. So in the left side, it should be acting in the anti-clockwise direction. Now let us find M2 in CD. Up to the section, we have only one load, that is the unit load. This is acting in the anti-clockwise direction, so it will be positive and the distance is x. 1 into x, we will get x. Now let us find M2 in dB. Here also, up to the section, we have only the unit load. This unit load is acting in the anti-clockwise direction, so it is positive and the distance is x. 1 into x, we will get x. Now let us find M2 in BA. The unit load is acting in the anti-clockwise direction, so it will be positive and the distance is x. 1 into x, we will get x. This movement is also acting in the anti-clockwise direction, so it will be positive. Now, in the delta L matrix, let us find delta 1L. The formula is integration of m1 upon ei dx. In this formula, let us apply the values. For CD, when we multiply m with m1, we will get 0. So no need to make the integration. For dB also, for m1, we have 0. So when we multiply m with m1, we will get 0. For BA, the limits are 0 to 8. The flexural rigidity is EI. We know the value of EI, 8000 kilonewton meter square. Let us apply that. Also, let us apply the values of m and m1. For the integration, we can use calculator. If you do not know how to make integration in the calculator, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and got the value of delta 1L. In this matrix, now let us find delta 2L. The formula to find delta 2L is integration of m2 upon ei dx. For CD, the value of m is 0. When we multiply 0 with x, we will get 0. For dB, the flexural rigidity is 2.5 EI. So we have to multiply EI with 2.5. The limit is 6 to 10. In the integrations, let us apply the value of m and m2. After making integrations, we are getting delta 2L. In the delta L matrix, we have found both of the values. Let us apply them. Now we are going to find delta matrix. In this matrix, first let us find delta 1, 1. The formula is integration of m1 square upon ei dx. For CD and dB, the value of m1 is 0, so no need to make the integrations. For BA, the value of m1 is x. After the integration, we are getting the value of delta 1, 1. In this matrix, now let us find delta 1, 2 and delta 2, 1. Both of them having the same formula, integration of m1 m2 upon ei dx. For CD and dB, the value of m1 is 0, so no need to make the integration. In BA, let us apply the values of m1 and m2. After the integration, we are getting the value of delta 1, 2 and delta 2, 1. In this matrix, now let us find delta 2, 2. The formula is integration of m2 square upon ei dx. In CD, first time we are going to make the integration. For CD, the flexural rigidity is 2.5 EI. So we have to multiply the EI value with 2.5. The limits for CD is 0 to 6. Now let us apply the values of M2. After making the integrations, we are getting delta 2, 2. In the delta matrix, we have found all of the values. Let us apply them. In this formula, we have found all of them. Let us apply. We can add these two matrices. After adding, we are getting this. For this matrix, we have to find the inverse. We can apply all of the values in the calculator and get the inverse. If you do not know how to make inverse in the calculator, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and got the inverse. Then we have to multiply these two matrices. After multiplying, we are getting RB and RC. Then let us apply the rule sigma V is 0 and find out RA. RA, RB and RC are acting upwards, so all three of them will be positive. The UDL and the point load is acting downwards, so both of them will be negative. After the calculations, we are getting RA 13.16 kN. Now let us find the moment in the point B, MB. I'm going to find the moment in the point B from the point C. In this case, I am moving towards left hand side. Clockwise will be negative and anti-clockwise will be positive. The reaction in the point C is acting in the anti-clockwise direction, so it will be positive and the distance is 10 meter. The point load is acting in the clockwise direction, so it will be negative and the distance is 4 meter. After the calculation, we are getting MB, which is equal to minus 12.3 kilonewton meter. In the same way, we can take moment about A and find out MA. Then, using the reactions and the loads, we can make the shear force diagram. Now we are going to draw the bending moment diagram. Before drawing the bending moment diagram, let us make the free movement diagram and the end movement diagram. For making the free movement diagram, we have to consider every span as a separate simply supported beam, and then we have to use these formulas and find the moments. Using those values, we can make these two diagrams. Then, using the end moments, we can make the end moment diagram. Now, let us combine the free movement diagram and end moment diagram so that we will get the bending moment diagram. Now, we are going to end this session. Thank you for watching this video.